Welcome back, guys. We're going to start by doing a couple example problems of Fnet equals MA, and then I'm going to do some more problems for you that are often seen on the AP test. Number one, what force is needed to accelerate a sled mass 55 kilograms at 1.4 meters per second squared on a horizontal frictionless surface? This is what they would just call a straight plug and chug. So it turns out I would need 77 newtons of force. Two, what is the weight of a 68 kilogram astronaut on Earth? Turns out it's 680 newtons. What would it be on the moon? What changes on the moon? The acceleration due to gravity. They're saying it's 1.7. That's a new one by me. On Mars, in outer space. In outer space, the acceleration due to gravity would be 0. How much tension must a rope withstand if it's used to accelerate a 1,210 kilogram car horizontally along a frictionless surface at 1.2 meters per second squared? Looking at my car's free body diagram, you would just have N, mg, and T. And so I would have that so T is going to be 1210 times 1.2. So 1450. I have a negative in there because the way I drew my free body diagram, my tension's going to the left, right? Number 9, a 0.14 kilogram baseball traveling at 35 meters per second strikes the catcher's mitt, which in bringing a ball to rest recoils backwards 11 centimeters. What was the average force applied by the ball on the glove? So I have F glove. And we have weight of the ball going down. So in the X direction, F glove equals MA. Well, I don't know what A is. I'm going to make a chart. My initial velocity is 35. My final would be 0. My displacement would be 11 centimeters, but that would be 0.11 meters. This should be negative because the glove is going to displace that way as it's giving a force this way, right? If you're catching something, you're going to go back slightly. So I can get my acceleration from kinematics. So I'm going to have let's say I can round up to 5,600. And so the force is going to be the product of the mass and the acceleration. So I got about 784, so I'll say 780 newtons. Oh, I wrote that down. That should be meters per second squared. All right, so only Fnet can be equal to ma. So you have to take into account all of the forces in one direction. That might just be one force, but it can only be Fnet. How do I solve these problems? Just like in kinematics, we went from one dimension to two. We're going to follow the same rules as we did for Fnet equals 0. Now you're just going to have to use your noggin and decide, do I have acceleration or is it in equilibrium? So the first thing is draw a free body diagram. Then if you have anything at an angle, you need to get rid of it. So you're going to resolve those into components. Then you're going to do an expression for your right minus left and ups minus downs. And the ones that are accelerating, you're going to set equal to ma. And then we just solve. Often you'll have the same ones in a problem. You have Fnet equals 0 and ma. When we had the sleepy dog, in the y direction, it was Fnet equals 0. The normal was balancing the weight for all of it. But in the x direction, we were accelerating, whether it was just me pushing that was accelerating it, or it was me pushing and friction opposing it that was accelerating it. All right, so we can solve a lot of our kinematics problems in the same way, just with the second law. So the first one is, I have a 0.5 kilogram ball. It's dropped from a 45-meter tall building. Ignore air resistance. What is the ball's acceleration? Does its mass make a difference? And I'm supplied with the dot. So I'm going to draw a free body diagram. What are the forces acting on this ball while it falls? Just wait. Is anything at a component or at an angle? Do I need to find components? No. So I'm going to identify my acceleration as happening in the y direction. And I'm going to say that in the y direction, Fnet equals ma. So I'm going to take my up forces minus my down forces. And if you look at this, mass cancels out. And so I'm going to get an acceleration of -10. Now, why didn't I put -10 in again? When I did minus down, I took into account the direction. Does this make sense? Yeah, if you drop a heavy thing and a light thing, if there's no air resistance, they should fall at the same rate. This shows you that it would just be g because the mass cancels out. It also explains why we often write weight as mg and not just w. All right, a 5 Newton box experiences 4 forces. A normal force, its weight. A 10 Newton force pulling it to the right, and an 8 Newton force of friction going to the left. I'm going to try to make this one a little bit less long than that one because this one's going to be 10. All right, what is the box's acceleration? I have 2 dimensions here. It's only going to accelerate where they're imbalanced. Looking at these numbers, you should be able to identify that one of them is unbalanced. That's going to be the x direction. I'm doing the right minus left. Get the acceleration by itself. I don't know what the mass is. But I do know that it's a 5 Newton box. So what would be the mass of something that has a weight of 5 newtons? Well, I know that weight is equal to mg. And so mass is going to be weight divided by g. So I'm going to divide this 5 by 10. And I'm going to get 0.5 kilograms. And so I'm going to have 2 divided by a half, which is 4. So that's going to be 4 meters per second per second.